Hello students. So today we are going to discuss about S block elements. As we know, our periodic table is divided in four different parts, and it is because of arrangement of electrons in respective atoms. So electrons enters in different orbitals of the atom, and that's why we can divide it into four different parts. If last electron of element enters into the S block or S orbital, then it belongs to S block. If it enters into the p orbital, then it will be p block element. And similarly, if last electron enters into the d orbital, then element belongs to d block, and same goes for f block. So in this lecture unit, we will discuss about the S block elements. In same book, we will discuss about p block element, not all of the p block, but columns of p block. And later in 12th, we will discuss about the remaining p block elements and d and f block. So in two books, 11th and 12th, we will completely discuss periodic table. If we check the periodic table, as we can see, it is divided in four different parts. All of the horizontal lines are called periods, and all of the vertical lines are called groups. So we can divide our periodic table in groups and periods. First two groups, that means 1 and 2, this belongs to S block, and we are going to discuss about these two groups in this unit. Later we have total 10 groups which belongs to D block. Then we have 6 more groups which belongs to P block, and later at bottom we have F block elements which actually belongs here. So this is our basic periodic table, and as we can see, all of the S block elements have one extra electron than noble gases. As for example, if we talk about the lithium, as we can see, it's number 3. So it has one extra electron than its previous element helium, which is noble gas. And we already discussed about that. All of the elements will try to gain noble gas like electronic configuration, because in noble gas electronic configurations all of the orbitals are fully filled, and that's why elements gain stability. So similar trend will be observed for all of the elements present in first row or column, sorry. So if we talk about the sodium, it is number 11. It has one extra electron than the neon. Then we have potassium, it has one extra electron than argon. Then we have rubidium, one extra electron then krypton. Then we have cesium, one extra electron then xenon, and francium, one extra electron then radon. So all of these electrons have only one extra electron than noble gas, and that's why they tend to lose electron to gain noble gas like electronic configuration. And that's why these elements are strong metallic by nature. Similarly, if we talk about the second column or second group, all of the group 2 elements contains two extra electrons than their previous noble gas. As for example, if we talk about the first element of second group beryllium, then beryllium contains two extra electrons than helium. Magnesium contains two extra electrons than neon, calcium two more than argon, strontium two more than krypton, barium two more than xenon, and radium two more than radon. So all of these elements contains two extra electrons than the previous noble gas, and that's why these elements also tend to lose electrons to gain stable electronic configuration like noble gases. That's why these elements are also metallic by nature. They are also strong metals, but their metallic characters are not as strong as the first group, because first group contains only one extra electron than the noble gases, and second group elements have comparatively stable electronic configuration. Why their electronic configurations are stable? If we compare sodium and magnesium, then we can see the difference. Electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. This is for sodium. And for magnesium, our electronic configuration is 1s2, 2s2, 2p6, 3s2. So as we can see, electronic configuration of sodium is unstable because it has partially filled s orbital, whereas Mg contains fully filled s orbital. If orbitals are fully filled, then they gain extra stability. So that's why all of the group second metals are comparatively more stable than group first. Group 1 metals are referred as alkali metals, and group 2 they are referred as alkaline earth metals. Now, reason behind the name is, let's talk about the alkali metal first. When we dissolve alkali metals with water, usually metal don't dissolve in water. So let's say when these metal reacts with water, they produces alkali solution, that means basic solution. That's why they're referred as alkali metals. And normally metal hydroxides and oxides are basic in nature, and non-metal hydroxides and oxides are acidic in nature. Similarly, second group metals are referred as alkaline earth metal because same thing, with water it produces alkali solution, and these metals are obtained from earth crust. Now let's talk about the properties of alkali metals. So as we discussed, these metals contains one extra electrons than noble gas, and that's why the last electron is loosely held with nucleus, and it is very easy to remove it. And that's why these metals forms M plus ions. Their electronic configurations are as mentioned here. These metals are highly electropositive. So as we can see, all of this metal contains one extra electron than the noble gas electronic configuration. And if we remove this one electron, then remaining electron shows noble gas like electronic configuration. That means this is the electronic configuration of helium. Then we have electronic configuration of neon. Then we have electronic configuration of argon. Then we have electronic configuration of krypton, and last we have electronic configuration of xenon and radon. So because of this one extra electron, these metals are highly electropositive. Then let's talk about the atomic and ionic radii. So we already discussed about the common characteristics of elements in periodic table in periodic table unit. Now one of the point was, as we move from left to right in a period, that means lower number to higher number but in the same period, because of increasing nuclear power or number of protons in nucleus, attraction towards the nucleus increases, and that's why with increasing atomic number, sizes shrinks or radiuses shrinks. Although electrons are increasing in orbitals, but still because of stronger attraction towards the nucleus, sizes will shrink. So that means it indicates s block elements will have comparatively larger size than the d block elements, and d block elements will have larger size than p block element. Although as we move from left to right, number of electrons, protons and neutrons are increasing, but because of stronger attraction towards the nucleus, electrons come closer to the nucleus, and that's why sizes shrinks. So that means left side elements will have larger size than the right side elements. So it represents all of the first group elements will have comparatively larger size than the remaining period. Because they are first, that's why they have comparatively less number of protons in their nucleus, and that's why electron feels lower attraction towards the nucleus, and we have larger sized particles which has comparatively lower mass. So that means S block elements, and specifically group 1 or alkali metals, they have very low density because their sizes are comparatively larger than the remaining period elements in period, and their masses are lowest than the remaining elements. So low mass and high volume, that means density will be lower. But as we move from top to bottom, whole new orbits will be added. In lithium, outermost orbit is number 2. Then in sodium, we have third orbit, then 4, 5, 6, and last francium contains seventh orbit. So as we move from top to bottom, sizes tend to increase because whole new orbits will be added. So it represents size of lithium will be smallest, and gradually with increase in size of francium will be largest. Now keep in mind most of the bottom elements are radioactive, and that's why in different studies we do not have much data available for these radioactive elements because of two reasons. First reason, they have very short lifespan. Radioactive elements tend to release radio particles, and because of that they will convert in simpler element. As for example, when radium shows its radioactive property, it produces radon and helium. Okay, so that's how it converts into some simpler atoms. So that's why they are unstable, they have short lifespan. That means you can get it from the nature but in very small quantity, so they are rare. And second thing, because of radioactivity, they are hard to study because radioactive particles are very hazardous for us. So we do not have much quantity of it, and they are very hard to work with. Now, similar to the atomic sizes, ionic sizes also increases as we move from top to bottom. That means size of ion of lithium will be smallest and size of ion of francium will be highest. All of this metal produces ions which has positive charge. That means lithium produces Li plus and francium also produces Fr plus. So, but we do not have much data available for francium, so let's not talk about it. Instead, we will talk up to the cesium. So cesium produces Cs plus ions and lithium produces Li plus, and all of these remaining elements do the same thing. So by losing electron, that means by reducing size. If electrons are removed from the orbitals, then sizes will shrink. So positive ions have comparatively smaller radii than their atom, and negative ions have comparatively larger radii than their atoms. So all of the ions have comparatively less radiuses than their atoms. That means size of atoms will be larger than their ions. Then we have ionization enthalpies. Now these elements are strongly metallic. That means their ionization enthalpies are comparatively very low because we can easily remove electrons from their orbitals. So considerably low, and as we move from top to bottom, their ionization enthalpies decreases because distance of outermost electron from the nucleus increases. Smaller size particles have comparatively closer electrons to the nucleus, and larger size particles have comparatively more distance with electrons and nucleus. So that means in lithium distance of electron and nucleus is least, and in cesium it is highest, and that's why electron removal in cesium is easy. So as we move from top to bottom, ionization enthalpies decreases. And second affecting factor is in larger sized particles, sizes overweights the increasing nuclear charge, and outermost electron is well screened from the nuclear charges. Now screening, that means inner electrons will almost neutralize all of the positive charge of the nucleus, so that outermost electrons feels very poor attraction towards the nucleus. That means we can say that inner electrons almost covers the attraction of the nucleus, and it is called screening. Then next, hydration enthalpy of alkali metal ions decrease with increase in ionic size. So we already discussed about the size of ion. Lithium has smallest ionic size and cesium has highest ionic size. So that means hydration enthalpy of lithium, it will be more, and for cesium it will be less. So lithium has maximum degree of hydration, and for this reason lithium salts are mostly hydrated. That means they attract water molecules strongly. Now let's talk about the physical properties. So all of these metals are silvery and white, soft and lightweight. Now these metals are lightweight because, as mentioned, their atoms are largest in their period, but their masses are lowest in their period, and that's why they have very low density. And low density, that means they are lightweight metals. Now these metals are soft because metals forms metallic bonds, and metallic bonds depends on number of electrons present in outermost orbit. As the number increases, strong metallic bond produces. But in this case we have only one electron in their outermost orbit, and that's why attraction is comparatively weak, and that's why these metals are soft. We can cut this metal with sharp edge tool like knife. Just like soap, we can cut the sodium metal or potassium metal. And because of weak metallic bond, their melting points and boiling points are also very low. These alkali metals and their salts impart characteristics color to the oxidizing flame. Now first thing, what is oxidizing flame? So oxidizing flame, that means if gas or fuel gets enough oxygen, it produces more amount of heat and less amount of light. It is called oxidizing flame. In our regular household burners, we have oxidizing flame which burns with blue colored flame. So it gets enough oxygen, and that's why it produces more amount of heat. And example of reducing, that means opposite of oxidizing flame, reducing flame is when we ignite the matchstick, it burns with yellow light or yellow flame. This yellow flame do not get enough oxygen, and that's why it produces more light but less heat. Similar example is candle. This is the example of burner used in our laboratory. It is known as butane burner. So as you can see, first flame is yellow and very bright. It is example of reducing flame. It do not get enough oxygen and it produces more light and less heat. Then as we increase the flow of oxygen, it will slowly turns blue and it produces more heat and less light. So last flame is oxidizing flame, which has blue color and very high amount of heat and less amount of light. First flame produces more light, less heat. Last flame produces more heat, less light. So when our metal or their salts come in contact with oxidizing flame, their electron starts to absorb energy from the flame. So first they will jump from lower energy orbitals to higher energy orbitals, and then they will get excited. Now after that they will come back to their initial state. So when they come back, they releases energy, and this released energy is in form of light radiation, and depending on the different type of metals and their salts, they produces different type of colors. And as mentioned, we have crimson red color from lithium, yellow from sodium, violet from potassium, red violet from rubidium, and blue from cesium. And that's why we can detect the metal if unknown compound is provided to you. And this is actual our practical. You will do this practical in standard 12 in inorganic qualitative analysis. In this type of lecture, you will be provided one unknown salt. That means it contains one positive ion and one negative ion. And in one of the test is known as flame test. In flame test, we will use paste of given compound, and then we will place it on oxidizing flame. If it contains one of this metal, then it will give one of this color. That means if you have potassium, then it will burn with violet color. Here we have example of flame test. As we can see, we have lithium, sodium, potassium, rubidium and cesium with their calcium salts. So as we can see, these metal produces these type of different colors with oxidizing flame. Some other metals also gives these type of colors, and their examples are as mentioned below. Calcium and other compounds of second group and certain D blocks also gives these type of colors. And because of that, one of the inorganic qualitative analysis test is known as flame test, and we can identify because of this property.